So what I'm going to talk about in this video is how to draw the molecular orbital diagram for difluorine. And so this is a homonuclear diatomic, right? So if we draw out the Lewis structure for fluorine, right, for F2, what we have is a single bond between the two of them, and then we have, three lone pairs all around in those cases. One thing we're going to see when we do the molecular orbital diagram is that that's actually not a really good depiction of what actually is going on, but that's fine. So we have F2, so what we want to do first is we want to put out the two atoms that are part of this on opposite sides of the page, right? So we have a fluorine over here, and then we have fluorine over here, and then directly in the middle is where we're going to draw then our MO diagram, right, for F2. So the first thing we want to do is we want to draw out the atomic orbital energy diagram for each one of the fluorines. And we only need to do the valence shell, right? We don't have to worry about the 1s orbitals, right? We're only going to be concerned with the 2s and the 2p. So I'm going to have my 2s for fluorine down here, and then up here, right, I'm going to have my 2p for that fluorine. And then the thing to make note, right, because both of them are fluorines, they're going to have the exact same energies for them, so they should match up in terms of exactly in height where you put them. So 2s, 1, 2, 3, 2p. So we have that right there. So the next step that we want to do is we want to fill in those atomic orbitals with electrons, right? So fluorine has 7 valence electrons, so we start filling those in. So we have atomic orbital diagrams that look like that for both of those atoms. Next step now is to start combining the orbitals, right? So what we're looking at is that we have, right, the 2s, and then we have, the 2pz, the 2px, and then the 2py. And over here, right, same thing over here, right? So we have the s, and then we have 2pz, 2px, and then 2py. Right, and so one thing that we know is that the s orbitals, right, they're going to combine together, and what you're going to form is a sigma bond, and so the sigma bonding orbital is going to be lower in energy than the atomic orbital energies that it starts off with, and then we're also going to form a sigma anti-bonding orbital, right? So every time you have a bonding orbital combination, you also have to have an anti-bonding orbital combination, right? So mathematically, they have to cancel out essentially in that regard. And the anti-bonding orbitals are always going to be higher in energy than the starting atomic orbitals that you get from it. So in that case, right, we would expect the sigma anti-bonding to be roughly right there or so, right? And so I'm just going to simply draw lines showing how everything is getting combined together. Right, so we have that right there. So the two s's are all combined to form their two molecular orbitals. And another thing I want to point out is that the number of molecular orbitals has to equal the total number of atomic orbitals that you have, right? So in this case right here, we have 4 atomic orbitals on each one of the fluorines, so that gives us a total number of 8 orbitals that are coming into it to form the molecular orbitals. That means that we have to have 8 molecular orbitals at the end of the day. That's a good way to keep track of how everything is going. So, but back to drawing it out, right? So, because we're looking at fluorine, as you may know, if you looked at your textbook or anything like that and have looked at the trends, what happens is that, after nitrogen, there's actually kind of a bit of a shift in terms of what the ordering of the molecular orbitals are, right? So for oxygen and fluorine, it's actually different for everything that, comes before, dinitrogen. So in the case of fluorine, right, the way that it works is that you're going to have the sigma bonding orbital, then the sigma anti-bonding orbital from the s orbitals. Then what happens after that is that you then have your sigma bonding orbital from the 2p orbitals that are going to be interacting. And then you have your 2 pi orbitals that form, and then you're going to have now your 2 pi anti-bonding orbitals, and then your sigma bonding orbital, anti-bonding orbital is going to be all the way up top, right? So these are all combining right here. Right, and so that's just the bare bones structure, right? That's essentially the molecular orbital diagram in that regard. Now all we have to do is we have to throw in, all of the electrons that we have that are going to be forming, filling up these molecular orbitals. And so to do that, we just simply add up how many electrons we have that are going to be, jumping in and forming these MOs. So if we look at the left, right, we have 7 electrons. On the right, for the other fluorine, right, we also have 7 electrons. So we would expect for the fluorine MO diagram to have a total of 14 electrons. So if we take those 14, right, and we start filling them in, following the Aufbau principle, Hund's rule, the Pauli exclusion principle, what we get is that, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Right? And so we filled it all the way in. And so what we can see is that, we fill in the sigma bonding orbitals, one of the sigma antibonding orbitals, and then the pi bonding orbital and the pi antibonding orbital. And so that right there, right, is the molecular orbital diagram. So, if that was what the question is, you're done. It may extend a bit further. It may ask you for, what the bond order is for this molecule. And so if we were to do that, right, the equation for that is you just simply add up the number of electrons that reside in bonding orbitals, and then you subtract out the number of electrons that reside in anti-bonding orbitals, and then you just divide that whole number by 2. So if we're looking here, right, what we have is we have 2 electrons that are in the sigma bonding orbital, we have 2 that are in this sigma bonding orbital, and then we have 4 that are in this pi bonding orbitals, right? So we have 8 electrons that are sitting in bonding orbital orbitals. And now the anti-bonding ones, if we add those up, right, we have 2 and then 4, right? So we come out to 6 in this case. And if we divide that by 2, what we get, right, is 2 divided by 2 is equal to 1, right? And so we get a bond order of 1, which matches what we see in our Lewis structure. So there's some similarities there, but the thing is that if you're thinking about, these like random lone pairs that are sitting on the fluorine, right, that's not actually a really realistic depiction of, what's actually happening in the bonding of the molecule. But that's how you approach, drawing the MO diagram for F2.